So it's my pleasure today to be presenting joint work with Gintari Jugaita, who's in the audience. There she is. So the starting point of this work is was the question, how does SGD work? There was a lot of work last year raising awareness about how little we maybe understood about SGD and how generalization worked in deep learning. So that intrigued us, and so we started thinking about it. So basically, there's this growing body of work arguing that SGD performs some sort of implicit regularization. And then from my perspective as a newcomer, the problem that I saw with this story was that there's no matching generalization bound that are non-vacuous in the regime of real data and realistic networks. So we went off and evaluated some of the bounds that are out there, bounds in papers like from 2015 that one might expect to be, and bounds from papers that are on deep learning. So you might expect to be non-vacuous, but they were far from non-vacuous. So that intrigued us. I was new to the area. So we also saw a number of papers that were reporting empirical findings, for example, flat minima, which I know is a controversial subject. And we saw a path, at least, to exploiting this structure, whatever that means, whatever that structure is. And I suppose at the end, when you see my PAC-Bayes bound, I will have formalized what I meant. We went about using PAC-Bayes bounds to exploit the structure to get bounds. So roughly speaking, here's a working definition. We're in a flat minima if the weights are such that the training error is relatively insensitive to large perturbations. I suppose you want to be in a local minima too, but it's actually not really relevant to our bounds. More concretely, what we're going to show is that the size, flatness, and location, sort of this kind of, I guess size and location may be redundant. So anyways, this aspect of minima found by SG on MNIST are sufficient to imply generalization. So we went out, and this is sort of an empirical thing. The minima that we found that SGD were returning to us, we could turn this around with the PAC-Bayes bound and prove a generalization result. And so then for our optimization colleagues, they could maybe then think about whether their optimization algorithms were implicitly regularizing that. And then you can maybe have an end-to-end story that goes from algorithm to generalization. So focusing on MNIST, we'll show you how we go about computing these generalization bounds that are non-vacuous for stochastic networks with millions of parameters. And maybe that's one more thing to emphasize, which is that we're not actually going to be focusing on bounding the literal SG solution, but we're going to be bounding the generalization of a small perturbation of this solution, which is the bread and butter of PAC-Bayes, I suppose. And then I'll close by talking about some more recent work where we try to tighten up those bounds. And the most obvious reason they're not tight is because the prior we're choosing is not depending on the data distribution. And we're going to obtain these bounds using a fair bit of computation, which is maybe a little bit different from is typical in the generalization bound community. So we're going to actually run SGD to obtain these bounds, and that's going to take hours. And this approach that I'm going to describe is very similar to something that was proposed by Langford and Caruana back at NIPS in 2002. But they were applying it to neural networks with 3 hidden nodes. All right, so I guess the key structure, or the key mathematical structure, we're after a non-vacuous generalization bound. So this is setting up some notation, but I also want to emphasize this plot. So we're after neural networks with small risk. Our tractor beam is going to be the empirical risk. We're going to chase that by, say, using stochastic gradient descent. And we're interested in the generalization error, so the difference between the risk and the empirical risk. And here's just a simple type of generalization bound. So the difference is upper bounded by some quantity. Maybe it depends on hypothesis space, how many samples you have, the confidence you want, the actual samples you got, and maybe the hypothesis that you're trying to bound. So here's a plot. We have this number coming down. So this is maybe this quantity as for everything fixed but m, or maybe everything fixed but some notion of complexity on your hypothesis that you've learned. And because imagine we're bounding a quantity that lives in 0, 1. So this gap is going to be self-bounded by 1. And so at some point this plot goes below 1. So we can draw this level set at 1. And so in this region here, the bound tells you nothing. And so this is what I mean by vacuous. When I talk about a bound being vacuous, I mean we're operating in this regime. And so while, say, the behavior of this curve might behave in a way that makes sense to you, until that, at least logically speaking, until that bound goes below 1, we haven't implied generalization. So when I was saying we were evaluating bounds and finding them to be vacuous, and what I mean is we were evaluating bounds and finding that we're in this regime. So it's interesting to consider what would it mean to get our bounds into this regime. Maybe it's just constants. Maybe it's a little bit of extra work. Maybe it's like don't use that particular bound for log 1 plus x or something. I don't know what it is. But I guess until we start pushing on this, we might not know what it is and how serious of a gulf it is. So I think it's useful to look. All right, so there's a lot of work of the form SGD is x, and then I think the implication is x implies generalization, and there's usually not a caveat on the second part. So SGD is acting like empirical risk minimization for large networks. SGD is doing some kind of implicit regularized loss minimization. SGD is approximate Bayesian inference. So the basic argument we've been making, and this is not the first time someone's made this argument, is that no statement in the form SGD is x is going to explain generalization in deep learning until we know that x implies generalization under real-world conditions. So we've undertaken a study like that. And it's preliminary, and it's sort of embarrassing, but now we have a baseline, and people can handily beat us, hopefully. So SGD is not simply empirical risk minimization. So this is a nice picture by colleagues at TTI. We heard from one of them earlier today. So they're training a network that's growing, and they're training larger and larger networks until they reach zero training error. So here after this point, SGD is behaving like an empirical risk minimizer. But we're not seeing any overfitting. So surely the performance of this is not entirely explained by, say, VC theory. And you can rapidly overfit on randomized labels too, so it's not just that the location of the data is easy in some way. So just to explain how far we are, MNIST has 60,000 training data, but a 2-layer fully connected ReLU network easily has more than 1 million parameters. So we're talking about orders of magnitude difference in terms of number of parameters in data, so that your PAC-Bayes are going to be far from vacuous. So not only can we not explain the behavior that this levels off, we can't even explain this gap. And it's really, you don't need very many nodes before, say, you're hosed on MNIST. MNIST already has 768 input units, and so by the time you hit 100 nodes in one layer, you're already toast when it comes to VC dimension. So we're going to focus on the generalization aspect of it because I don't really know much about the optimization aspect. So I've already argued that on MNIST, with realistic networks, VC bounds aren't going to be the tool to imply generalization. We've done some work. You can find this in our UAI paper. Classic margin and norm-bounded raw macro complexity bounds, at least the ones that existed before the start of the summer, don't imply generalization, though it's interesting to evaluate some of these new ones that have shown up recently. Being Bayesian doesn't imply any sort of generalization, not out of the box. You can easily get Bayesian neural networks to overfit. So what we're going to do instead is we're going to use PAC-Bayes bounds, and we're going to exploit the structure that people have been talking about, and it's a little fuzzy, so this notion of flat minima. But here I'm emphasizing it's going to be not only the flatness, but maybe the location of that minima. And these minima are going to be ones that we find in the wild, so this is a bit of an empirical thing going on here. But we can then apply a PAC-Bayes bounds to these minima we find in the wild, and these are kind of wide enough and close enough to some point that I'll specify later, such that we get generalization. My understanding is that actually a number of authors are arguing that SGD in particular, but not certain variants of SGD, are maybe drawn towards regions that satisfy some of the hypotheses that we require for our PAC-Bayes bounds to kick in. So maybe we do have an end-to-end story. And I guess I'm sure we'll bring up to discuss flat minimum in the question. So I'll leave it at that for now. And then I'll just re-emphasize that our bounds are going to require a fair bit of computation because we're going to kind of test the neural network and understand the sensitivity of its predictions to its weights. We're not going to use an infinitesimal analysis of that. We're not looking merely at the Hessian. We're going to do quite a bit of computation. All right, so flat minima. So here's a picture of flat minima on the left, and here's sharp minima on the right. Good, we all understand. So So the basic intuition of flat minima, at least from our perspective, is the training error in this flat minima is insensitive to relatively large perturbations. And so the notion of largeness is going to be relative to some fixed point, namely just to foreshadow where you've placed the prior. All right? So you have to have a relatively large perturbation relative to that distance to where you centered your prior. That's going to pop out in the analysis. So the idea that I can, say, perturb the solution and not incur too much excess risk, whereas here, if I perturb the solution, I incur quite a bit of excess risk relative to where I started. That means that a randomized classifier situated here is going to have roughly the same good performance as the one that was in the minimum. So that's the basic idea. And so we can study the generalization error of that randomized classifier that we fit into this big valley using PAC-Bayes theorem. So here's a statement in mathematics of a kind of a general form of a PAC-Bayes theorem. This is like one that I guess I first saw it in a paper by Lever et al. But in words, this is, and there are experts in the room, so this is for the non-experts. So the PAC-Bayes theorem is telling me for any data distribution D, for any prior randomized classifier P, and this is a prior in this kind of nuanced sense. It can be nonsense, but that's essential power of PAC-Bayes. It can be nonsense. It doesn't have to be a subjective prior. So for any prior randomized classifier P with high probability over M IID samples, for any posterior randomized classifier Q, not necessarily one computed by Bayes' law, the generalization error of this randomized classifier Q is bounded in terms of the KL divergence between Q and P. Well, that's the essential term that I care about. So going back to this picture, so there's two terms we care about. We care about the KL being small, and we also care about the empirical risk of Q being small. We need both of those together. So if this point is good, and a random perturbation doesn't increase the risk too much because I'm in this flat minima, then my randomized classifier's risk is going to be good. And then the KL term, because it's such a big valley, I can expand my Gaussian, and I can have a large volume. And if I'm not too far away from where I started, then this KL term is going to be small. So those two things combine. Now you can tell that story to yourself, but then it could be the case that on real data, these numbers add up and you get something bigger than 1. And just to foreshadow, we're going to add up these numbers and get a number that's less than 1. So that's the empirical finding, really. It might not happen on another problem. We've only studied a few problems. But so far, we have found enough volume near the solution that SGD finds to inflate this big Gaussian and get a generalization bound that's less than 1. So just a bit more formally, so we have this hypothesis class of, I wrote binary classifiers, but this generalizes as 0 and error for multi-class. And the randomized classifier, you can think about it as some distribution in the hypothesis space. That's what I was talking about earlier. And so this is what I mean by the risk of a randomized classifier. It's just averaging, it's just imagining that you draw a classifier and then label a point. PAC-Bayes are among the sharpest, I guess, in practice. That's what I understand it to be true. So here's a version of PAC-Bayes theorem due to Catoni. It's not a particularly good parameter. It's a specialization of his theorem. Don't blame him for it. But I've chosen it because everything's going to work out nice for the next slide. So our approach is the following. You give me M data. I'm going to build this empirical risk surface. And then I'm going to run SGD. And SGD is going to find some minima. And then that's SGD at the end there. And then I'm going to inflate this Gaussian. And I've drawn the level sets here, and I've drawn it like this just to suggest the case that I might blow right past the level set. Like I'm not fitting this in the local Hessian, like curvature or whatever. I'm inflating this to minimize bound. So, no, I'm going to allow it to shift a little bit, and then afterwards we notice that it doesn't shift very much. Right, because SGD might find itself sort of at the edge of a large volume, and then we want to kind of move it into the middle. Okay, that's a good question, though. And at the end of the day, what the numbers come out is that the network that we find in this region near the SGD solution, the stochastic network, its risk is bounded by 17% with high probability. Now, its actual risk is closer to 3%, which is pretty bad. 3% is pretty bad for MNIST. And part of the reason that is so high is because the bound is so loose, and I'll talk more about why the bound is so loose. Now, this number 17 is loose as well. I think people who maybe don't know what these bounds generally come out to, might be kind of shocked to see that number. But I was actually very pleased to see that number. So when you have this PAC-Bayes bound, you can think about optimizing it. Yes, please.
On that number,
Great question. It's MNIST, so it's I think it's 50,000 because we're not using the validation set.
Okay. What's square root of 50,000?
250-ish.
So like the best you could ever possibly hope for is 1 on 250.
Yeah, which is it's closer to 1% or something like that. Yeah, or that's like 0.01 or something. Yeah, yeah. So we're way above what, say, just a straight up. I actually know the answer, and I just want to verify the risk empirically. Yeah. And we think about square roots a lot when we're trying to see if these bounds make sense. So, yeah, it's a great question. It's a good way to calibrate. So we're far away from like noise level. All right. So you can these PAC-Bayes bounds, you can treat them as a way to say choose a classifier. So, and the reasoning goes, well, I can choose this PAC-Bayes bound is a uniform bound over all randomized classifiers, so I can indeed optimize the bound, and that's valid. So I can find a provably good bound by optimizing the PAC-Bayes bound. And say for Catoni's PAC-Bayes bound that I just showed you, the optimization problem looks like this, which for, say, the Bayesians in the room is going to look awfully like a variational inference objective. Indeed, the optimal Q is known as a Gibbs distribution. It satisfies this equation, so it's absolutely continuous with respect to the prior P that you fixed before looking at the data, and it has this particular form, which looks like Bayes rule. Indeed, it's called like a generalized Bayes rule in the information theory community. That's my understanding after reading Peter's stuff recently. And under log loss and say choosing tau to be equals to m, then this term is what the sort of variational Bayesians call the expected log likelihood, and this objective is the elbow. And then you have this characterization of the optimum that if you take the supremum over distributions Q, then this number ends up being this generalized log marginal likelihood. And indeed, under the same conditions here, when this was an elbow, then this is your log marginal likelihood. So, and these last points were kind of very nicely laid out by Germain et al. Recently. Now, so the optimal answer, we know it analytically. Here's the answer for this particular PAC-Bayes bound. So it'd be nice to use this one, but this is generally intractable. So I think in PAC-Bayes theory, you often find yourself knowing what would be the optimal thing to do, but then you're hamstrung a little bit by computation. Or at least that's how I think about it. And so just as the variational Bayesians do, we can say think about optimizing this over a subfamily. So that's what we do in our work. So we're going to optimize this over, so we got to do an optimization. We're going to replace, say, the non-differentiable loss with something that's differentiable. When we get down here, we're going to look over the subfamily of Gaussians that are axis aligned, and we're going to be trying to find their mean and their diagonal covariance. So it ends up with an optimization problem like this. For our prior, we're going to choose a Gaussian, but we're going to also put a prior over the scale of its variance. But we're going to deal with that. We're going to deal with that with a union bound, and so we end up with this is our optimization problem at the end of the day. So for people who kind of stare at these things for a long time, you see something that looks like L2 regularization, but we've chosen to regularize back to the initialization that we chose for for SGD. So that gained us, I kind of forget, gained us like 4 or 5 extra generalization points doing that. It was something naturally that we did because we were so worried about symmetries. So that we started with that. And then this term is trying to make sure that your posterior variance is not too large relative to your prior variance, because you don't want your and this term is trying to make sure that your posterior log volume of the log volume of your posterior is large. So there's this tension. This is basically trying to get the two Gaussians to overlap as much as possible. So that's your objective. And people will recognize, say, salient things in there. Yeah, please. Good question. So I'm going to use a union bound to choose lambda from a discrete collection. But then I'm going to perform this continuous optimization and then round and then apply my union bound to be able to have chosen lambda in a data-dependent way. So it's like a poor man. So
Union bound over lambdas.
Yeah, union bound over lambdas. It would have been better to have P be a scale mixture of Gaussians, but I didn't know the formula for a KL in that case, so I just used a union bound. We just used a union bound. Okay, so these are the numbers you get. just as we saw earlier in that work by TTI, you can get the training error for neural networks on MNIST down to 0 error. Ignore this column for now. This is 1, 2, and 3 hidden layers, 600 units each. So these networks already have 400,000 parameters, 800,000 weights, and 1.2 million weights. using a bound that Peter Bartlett gave me, we can upper bound their VC dimensions by 26, 66, and 121 million. So that's pretty much useless. Now we optimize the stochastic neural network near the and we end up finding empirically that stays near the SGD solution. So you're inside a little pocket already. And what we find for the PAC-Bayes bounds is, say, for the one neural network, our risk bound comes in at 16%, 2 layers 18 and change, and 3 layers 20. All right, so what this demonstrates, I guess, I'm trying to say a tautology here, that for the type of flat minima that we just found in practice, the PAC-Bayes theorem returns you a non-vacuous generalization guarantee. It's a good question. We could be doing a worse job optimizing. The weights could be exhibiting more dependence, which our axis line Gaussian is not able to capture. A whole bunch of reasons. I don't think we know yet that it should be increasing. So that's a little disappointing of an answer, but I think that's the truth. So these bounds are loose, but at least at the moment, these are the only bounds that I see in my own eyes that are less than 1. All right, so all this work up until this point is focused on SGD. But maybe we shouldn't be focused on SGD, because SGD is pretty dangerous. So there's this paper, Understanding Deep Learning Requires Rethinking Generalization, 120 citations in its first year. One of the cool things that it pointed out was, and I'm only going to discuss one of these bullet points, and it's this line right here. If you can run SGD on random labels on your 50,000 element data set, and it'll happily achieve 0 training error for those random labels, which is pretty scary, because SGD just obtained 50% risk if you binarize that problem, or like 90%. So that's pretty bad overfitting. So maybe we shouldn't be using SGD. And I often wonder whether the received wisdom that neural networks need a lot of data might be due to the fact that our learning algorithms are like raring to overfit on the data. So it's interesting to ask whether we can design algorithms that provably don't overfit, but also are not terrible. Because there does seem to be a tension between these two things. And so I guess at a high level, I'm interested in that tension and whether it's impossible to ever have both or almost have both. So this guy's thinking about better algorithms, and we're thinking about, and we come across this entropy SGD work. They make claims about having better generalization than SGD. There's a connection they outlined to flat minima, so we were intrigued and looked at it. And so we thought, okay, maybe this is let's study a different algorithm, maybe one that doesn't overfit as rapidly. So what is entropy SGD? It replaces stochastic gradient descent on the empirical risk surface with stochastic gradient ascent on the local entropy surface. So here's a rough picture. You have this empirical risk surface, which is maybe jagged. And when you look at the local entropy associated with this risk surface, so here's the empirical risk. When you look at the local entropy now, transformation of the surface, it emphasizes the flat minima. Or at least that's the two-dimensional or the one-dimensional picture. I actually don't entirely understand the high-dimensional picture. Maybe no one does. All right, so that's the idea, though, that this surface emphasizes flat minima. Ergo, it should work better. So in actuality, if you run this algorithm, it will overfit random labels even faster than SGD, which is a little scary. But we sort of understand why it was overfitting so badly now. So I'll walk you through this. So studying this algorithm a little bit more, we came to the realization that it has this connection with PAC-Bayes. So here is the objective that entropy SGD is optimizing again. And this might look familiar. It looks like a log partition function. Indeed, it's almost a log partition function of a Gibbs distribution for the empirical risk where you have a Gaussian prior. So indeed, it's not hard to show. You just use like the Donsker formula. And also this calculation has been done, I'm sure, 100 times in various papers. I'm sure Peter knows 4 or 5 of them. That maximizing this local entropy with respect to W corresponds to minimizing a PAC-Bayes risk bound on a Gibbs posterior with respect to that prior's mean, W. which sounds pretty cool, but it's also totally against the rules. You cannot optimize your prior for your PAC-Bayes bound based upon the data. Of course, then again, your empirical risk was a great unbiased estimator of your risk until you started optimizing it, right? So this is sort of the same sort of thing. Now, you are allowed to choose your prior based upon the data distribution. Just normally you don't know what that is, and so that sort of is useless unless you have a very clever way of bounding that KL divergence, because that's all you really need to know about your prior. But we had another idea, because in this situation it's a little bit hard to use local priors, though I'd love to discuss this later with people. So the idea was, well, if we take a peek at the data but don't look at it too long, maybe that short peek will give us a good insight for a good prior, and then maybe our bound still holds. And we can formalize that idea using differential privacy. So it is almost a corollary, it's a very simple exercise from a basic theorem in differential privacy, one due to Dwork and others, that if I have a random measure chosen on the basis of the data, and the way in which this choice is made is epsilon differentially private, then I have this PAC-Bayes bound. So we applied this to, say, the KL one by Langford and Seeger. And all that's really changed is over here. So you see that we have an epsilon squared, that's the differential privacy squared, multiplied by m, ignore this max, because this is usually larger, so that m kills m, and you have an epsilon term showing up in your excess risk, your epsilon squared, or in your gap. So you have to be sufficiently private for this to be useful. Now, SGD on the local entropy surface is not going to be private, but you can get approximate differential entropy if you run, say, SGLD, which means doing SGD, but every single time adding some isotropic Gaussian noise. All right, so here comes some hand waving. If you run SGLD long enough, subject to a condition which is not quite true, which is that apparently someone just told me this, that the noise is isotropic from the stochastic gradient, then SGD converges in distribution to a epsilon differentially private mechanism called the exponential mechanism, which kind of makes sense, or the hand waving kind of makes sense. So SGLD, if you long it run enough, it's going to be targeting the stationary distribution. It's going to forget where it started. And it's going to be sampling from this quantity exponentiated. And so really what we need, in order to determine the privacy, we look back in here, what we realize is actually the privacy of this, or releasing an element from a distribution that's proportional to the exponential of this, is going to be garnered entirely by, say, a bound on your loss, or a bound on your empirical risk, and the size of this quantity tau. So we can play with these two quantities and determine up to this approximation that SGLD returns something that's actually purely differentially private. We can dial in just how much we look at the data. If we look more at the data, our bound loosens. If we look less at the data, we have a worse prior from having cheated. All right, so this is totally legit. Pretending SGLD is purely differentially private is cheating. There exist purely differentially private analyses of SGLD. They're just way too loose. And none of them take advantage of the fact that you expect SGLD to start mixing at some point. And so I suspect they're also, I expect these bounds, not only the bounds are too large for our purposes, I believe they are loose. All right, so we make this coarse approximation. And so that allows us to plug in a prior after looking at the data. And what that prior is going to be, it's going to be the location of a Gaussian. And so so if I didn't have this Gaussian here, this would just be the Gibbs distribution, which would be like, God's classifier. Go where the risk is lowest. And I can crank up tau and really focus on where the risk is lowest. So when I add this Gaussian here, and say I crank up this term gamma, then what I'm doing is I'm saying, nope, I think the best solution is in this little area right here. I've dropped a little sharp Gaussian. And then this tilts it towards choosing, in this local region that I've just demarcated here, this biases it towards choosing solutions with low risk. This, for a very large gamma, I believe that you could sample from this. Without this sharp distribution here, this Gaussian here, I don't think you can pretend that you can have a computationally effective mechanism for sampling from this. But if this Gaussian is sharp enough, then I think that's reasonable. right, so this is what we find making these approximations. So if you go back to MNIST, then on a fully connected, I think this is 3-layer network, your actual training error of SGD and the SGLD kind of local Gibbs posterior. So that's a Gibbs posterior for a very localized Gaussian. These are right on top of each other. And here's our generalization. Here's our bound on the risk. So it's a little bit hard to read this, but this one bouncing along here is the PAC-bound one. And you can also, using differential privacy, apply other types of bounds. The PAC-Bayes bounds tend to be the tightest by a little bit. Yeah, so these are fairly similar results for slightly different networks. So here is a convolutional neural network, which is performs better, has fewer parameters, and we get better generalization performance and tighter generalization gaps. Again, the PAC-Bayes bounds are showing up as the tightest. This is a picture of how that tau parameter affects things. Let me jump ahead here. So I said before that the way that you set this tau affects the differential privacy, which then affects the size of the generalization gap. And indeed, if you don't set that tau parameter correctly, these are being run on random noise, and so they should hover up here. And indeed, the math says this parameter is safe, and these parameters are too large, and indeed, they're starting to overfit. And so this is entropy SGLD properly configured, running on random data. So its empirical risk is hovering just below 50%. The generalization gap is hovering a little bit above 50%. So that's sort of a sanity check. If this was way off, then this would be ridiculous. So the way I think about these results is, so I'll go back a slide. So even though this is, say, 2% error, that's still pretty bad because state-of-the-art for MNIST, which is obviously being overfit, but I would suspect state-of-the-art for MNIST is well below 1%. And so we're off by say, a factor of 5 here. Yeah?
Is this for the stochastic classifier, or is this
The darker lines here, I can't tell you the color. Is that purple? Blue? These ones that say Gibbs. These are for the stochastic classifier. And this line right here, is that yellow? Something. That one is the PAC bound on that classifier. Okay. Anyway, so this is using this slightly unrealistic privacy assumption about SGLD. But even then, our risk bounds are quite far away from. Even then, we're severely underfitting. So by optimizing this bound, we're still severely underfitting. And why that's happening is because in order to not blow our privacy budget, we're having to look at the data very, very little to choose this prior. And so in some sense, what we learned from this experiment is differential privacy is not the right way to formalize cheating and looking at the data to have a data-dependent prior. Now, you can actually replace all this mechanism with local bounds and differential privacy as well, and that doesn't really gain you anything as well. So I guess the experiment says here is this gains you something, but it's not enough, and so we have to eventually ditch the differential privacy to get some other mechanism having data-dependent priors, and that's or data-dependent regularization in the notion of that work of yours recently. All right, so I'll stop there. I'm a little over time. So in conclusion, we show that the flatness and location of minima that we're empirically we're finding SGD narrows in on MNIST. These are sufficient to imply generalization using PAC-Bayes bounds. We show entropy SGD optimizes a prior in a PAC-Bayes bound, which is not a valid way to go about, but we can sew this up by using differential privacy. We can give a private version of the PAC-Bayes theorem, which accepts a differentially private prior. And then we make this coarse approximation, assuming the SGLD achieves the privacy of the stationary distribution to which it's weakly converging. That's a little bit much to swallow, but subject to that approximation, we get bounds that say aren't being violated too frequently and behave in the right way. As we're tuning that differential privacy parameter to extend our generalization gaps and shrink it, we are seeing, say, behavior in random data behaving the right way. If we say you shouldn't overfit, then we hand it random data and it's hovering right there next to 50% error. It won't overfit. So I view this as a step in the right direction at least. Thank you. Yeah.
That's why I was surprised by your Python increasing as you increased that.
Yeah. I wouldn't read too much in. Is this working? I wouldn't read too much into that increasing yet until we explore it more.
So what do you think about that result?
The compression. Well, what I will say is there is a connection with information, which is that if you plug in, so cation E has these local priors, which is the expected posterior. If you plug that into the KL term, then the expected contribution of that term is the mutual information. So there's a connection with information theory. But just like finding flat minima is a sufficient condition. Right? It's easy to transform a flat minima through reparameterization of the network to a sharp minima. Of course, that's going to generalize exactly the same because you've done nothing to the function. We ought to be working on the equivalence class, but it's very hard. The Gibbs distribution works on the equivalence class, but computationally it's very difficult to work on equivalence classes, it seems. Mutual information is also not necessary because, for example, I can train a neural network, be assured by some other means that I have very good generalization, and then I can figure out how sensitive my solution is, go down to the millionth digit or whatever, and encode my data. So now my mutual information is maximal. And so I've just shown by hand waving that mutual information is not necessary. So I'm not sure. I'm not sure if we can even ever expect, or I'm not really sure when to expect sufficient and necessary conditions. So yeah.